Hello everyone. In continuation of the macro videos for the control tutorial, in this video I will solve some problems from last exam. In the first question, we are looking for a transfer for the Laplace transform of a given system signal, as shown in figure. To find the Laplace transform of this function, we need to look at the definition of Laplace transform. According to the definition of the Laplace transform of function ft is integration of ft e minus st dt when t is varying from 0 to infinity. And according to the figure, the function ft can be defined as ft equal to 0 when t is bigger than 0 or less than 2, 1 if t is equal or bigger than 2 and less than 3, and again 0 if t is bigger than 3. So if we implement this function ft to the definition of the Laplace transform fs, we will have this relation. Fs is equal to integration of 0 multiplied to e minus st dt when t is from between 0 and 2 plus 1 multiplied to e minus st dt when t is between 2 and 3, and again plus integration of 0 multiplied to e minus st dt when t is varying from 3 to infinity. So it's obvious that the first and second integration are 0, so we have just the first and third integrations are 0, so we have just second integration. So the integration of e minus st dt when t is varying from 2 to 3 will be minus 1 over s e minus st. Substituting the value initial and final values, we will have fs equal to 1 over s e minus 3s minus e power minus 2s. In the part B of question 1, again it's asking to prove that the Laplace of cosine omega t is equal to s over s squared plus omega squared. To solve this or to prove this relation, we have two approaches. The first one is the definition of a Laplace transform. So using the definition of the Laplace transform, we know that Laplace transform of function cosine omega t is integration from 0 to infinity e minus st cosine omega t dt. To solve this integration, I use the integration by part by defining u and v function u and v as the e minus st and cosine omega t. I have the first part of the integration by part as e minus st sine omega t over omega from 0 to infinity minus integration of minus s e minus st sine omega t over omega dt. If I substitute the initial and final values for the first part of integration, I see that this integration is the value of this part is 0. So the remaining part will be minus will be the second integration. Since s and omega are constant, I can take out the s and omega. Minus will be cancelled out with this minus. So I have s over omega integration of 0 to infinity e minus st sine omega t dt. Again, I need to further solve this integration by integration by part. So if I use the same approach, I will have this integration equal to s over omega e minus st minus cosine omega t over omega from 0 to infinity minus integration 0 to infinity minus s e minus st multiplied to minus cosine omega t over omega dt. If I substitute 0 and infinity in this function, I will have s over omega multiplied to 0 minus 1 over omega. In fact, cosine omega t, this function when t is infinity is 0, and when t is 0 is 1 minus 1 over omega. And if you look at this function, if you look at this integral and compare it with the first integral we have, we see that this integral, the first one, is equal to minus s over omega fs. So by considering this relation and considering that fs which is the Laplace of cosine omega t, is equal to s over omega 0 minus 0, or in fact 0 plus 1 over omega minus s over omega fs. If I consider this one, I have fs equal to s over omega square minus s square over omega square fs. If I bring this fs to the left hand side of the relation, I will have a 1 plus s omega over omega s square omega square multiplied to fs is equal to s over omega s square. If I get the common denominator for these fractions, I will have fs equal to s over s square plus omega square, which shows that the Laplace of cosine omega t is equal to over s square plus omega square. For the alternative method, I use the transform of derivatives. Theory of the transform of derivatives. Theory of transform of derivatives says that Laplace of second order differentiation of function f is equal to s square f of s minus s f0 minus f prime 0. So if my function ft is equal to cosine omega t, the second it means that and if I assume that t is equal to 0, so f0 is equal to 1. The second derivative of ft is dft over dt, which is equal to minus omega sine omega t. If I substitute the initial condition again, I will have f prime 0 equal to 0. So the second derivative of ft is equal to minus omega square cosine omega t. If I assume that the Laplace of ft, which is the Laplace of cosine omega t, is equal to fs, and by comparing here, I see that the second derivative of ft will be equal to minus omega square f of s by comparing this one, because the Laplace of ft is Laplace of cosine omega t is fs, and since omega square is constant, minus omega square is constant, the second derivative of the Laplace of d square ft dt will be equal to minus omega square fs. From another hand, I know from the theory of the derivatives, the Laplace of the second derivative of a function is given by this relation. So if I equal this one to s square fs minus s f0 minus f prime 0, and since f0 is 1 and f prime 0 is 0, if I substitute the values here and rearrange the equations, the relation, I will have minus omega square fs equal to s square fs minus s. If again I bring fs to the left hand side of the equation, I will have s square plus omega square fs equal to s. Thus fs is equal to s over s square plus omega square, which is the end of proof of this relation. In part C of the question 1, we are looking for the solution of a given differential equation, which is dyt over dt plus 3yt equal to ut, with assumption that ut is unit step function, is a step function with amplitude of 2, and if given initial condition y0 equal to 1. To solve this differential equation, again I use the theory of transformation of derivatives theorem, assuming that the Laplace of yt is ys, and by the transformation of derivative theorem, I know the Laplace of dyt over dt is sys minus y0. Initial condition is 1, y0 is 1. So and I know that the Laplace of ut step function will be 2 over s. So the Laplace transform of the whole differential equation will be Laplace of dyt over dt plus 3yt equal to ut, which is sys minus 1 plus 3ys equal to 2 over s. If I reshape the relation and factor out ys, I will have s plus 3, ys is equal to 1 plus 2 over s. So ys is equal to 1 over s plus 3 plus 2 over s plus 3. As you see here, the Laplace transform of response is composed of two fractions. The first one is because of initial condition, the response due to the initial condition, which is known as the free response. And the second part is response due to the external force, which is a step function in this case, which is known as the forced response. So if you solve these equations, your time response will be composed of these two, the Laplace inverse transform of these two fractions. To solve this one, I need to use the partial fraction for the second response, or for the forced response. After applying the partial fraction, my ys will be equal to 1 over s plus 3 plus 2 over 3s minus 2 over 3s plus 3. If I use the Laplace inverse transform and I use the table for the Laplace inverse transformation, I will see that yt is if I further simplify these relations, and if I use the table, I will find the Laplace inverse of ys, which is yt, is equal to 2 over 3 minus 1 over 3 e minus 3t. So for the second question, it is asking that dynamic of a car is given by this second order differential equation, which vt is the velocity and ut is the input. The question says that the initial conditions are given, v0 is 1 and v dot 0 is minus 1. We are looking for the transfer function of gs equal to vs over us, and as well as we need to sketch the position of its poles in s domain. Again, we need to solve this differential equation, we need to use transformation of derivatives theorem. So after applying the transform of derivatives theorem, I have the Laplace of the differential equation as s squared v of s minus s v0 minus v dot 0 plus 2s v of s minus v0 plus 4 v of s equal to s u s plus us. If I apply initial condition, I will have s squared plus 2s plus 4 multiplied to vs equal to s plus 1 plus s plus 1 us. So again, as you see, vs is composed of two fractions, one due to the initial condition, another due to the external forces. But we are looking for the transfer function of vs over us. If you remember, the definition of the transfer function is the ratio between output over input when all initial conditions are 0. So to find the relation transfer function of vs over us, we need to ignore the first fraction due to the free response. So if I ignore this part, the free response, I will have g of s equal to vs over us, which is equal to s plus 1 over s squared plus 2s plus 4. In the second part, we are asking to sketch the location of the poles. As you know, the poles are the roots of the denominator or characteristic equation. By finding the roots of the characteristic equation, we see that the roots are, we have two complex conjugate roots equal to minus plus minus 1.7 j. If we sketch the poles on complex plane, as shown here, because as we see, because both poles are in the left hand side of the imaginary axis, the system is stable. For part B, we are looking for the simplified transfer function from ys over us. To simplify this block diagram, we first look at the feedback loop given here between G2S and G4S. If we consider this feedback loop positive feedback loop, we see that the transfer function will be equivalent transfer function will be G24 equal to G2 over 1 minus G2 G4. So if we substitute this feedback loop, positive feedback loop with this transfer function, we will have G1 and G24 in series. So the equivalent transfer function of two series block diagram or transfer function will be their multiplication. So G124 will be equal to G1 multiplied to G24, which will be equal to G1 G2 over 1 minus G2 G4. So after applying this one, the equivalent transfer function, the resultant transfer function will be in this form, will be a negative feedback. In feed forward path we have G124S, and in negative feedback we have G3S. If we use the negative feedback loop equivalent function, we will have G1243 equal to G124 over 1 plus G124G3. If we substitute if we substitute the transfer function of G124 and G124 and G3 in this transfer function, we will have this relation. If we further simplify this transfer function, this ratio, we will get G1 G2 over 1 minus G2 G4 plus G1 G2 G3. If we substitute the values of the given transfer function for each block, G1, G2, G3 and G4, we will have 1 multiplied to S over 1 minus S multiplied to S minus 1 plus 1 multiplied to S multiplied to 1 over S. This S will be cancelled out with this S, so the resultant of this parenthesis will be 1 plus 1, I have 2. So the equivalent ratio will be S 1 minus S, S minus 1 plus 1. So the final simplified transfer function is in the form of minus S over S squared plus S minus 2. Okay, in the question 3, it has been asked to explain why derivative controllers are never used on their own. It also, a transfer function of a system is given, and it asks to find the time response and sketch the time response and estimate the time response based on this given input function. And also we need to find the characteristic equation of the system. So for the first part, I need to mention that the derivative controller is always used in conjunction with proportional or integral controller to increase the damping and generally improves the stability of the system. So the reason we use derivative controller in our system is to improve the stability of the system and improve the response of the system, because derivative controllers increase the speed of the response. However, they have two main issues that hinder their implementation on real application or the use of just derivative controllers. The first one is that if we just in practice apply the pure derivative controller, if the output derivative or output of the error is constant, the output will be always 0, and the controller doesn't do anything. Another problem with the derivative controller is their effects on disturbance amplification. Actually, derivative controllers amplify the errors or the disturbances if they include, specifically if they include higher frequency components. For example, look at this function. Assume I have this disturbance or signal equal to 0.01 sine 100t. If I get the derivative of this signal, I will have minus 0.01 multiplied to 100 cosine 100t. If I do this amplification, you see I have minus 10 cosine 100t, which is much bigger than this amplitude given here or the amplitude given here. So this is the reason we can't use the derivative controller on their own, because they amplify the amplitude, they magnify the amplitude of the disturbance signals. So for the second part, or part B, GS is equal to Q0 over Qi, which is 2 over S squared plus 6S plus 5. If I applied Qis as 2 over S, I will have Q0S equal to 4 over S squared plus 6S plus 5. If I find the roots of this second order polynomial, I see I have two simple roots, one S equal to minus 1 and another one S equal to minus 5. To solve this, to find the time response of this Laplace function, I need to use the partial fraction. Applying the partial fraction, I will see that I will have three components: 4 over 5s minus 1 over s plus 1 plus 1 over 5s plus 1. If I take the Laplace inverse of this fractions, I will have yt equal to 4 over 5 minus e minus t plus 1 over 5 e minus 5t. If I sketch the response by hand or by computer, the response will be in this shape. As you see, the response looks like a first order system. In order to estimate a rough estimate of time constant, I need to find the slope and the points at which this slope cross the constant, the final value, and the timed axis. As you see here, the time between these 2 points will be tau, or time constant, which is almost equal to 1.8 second. For the part C, the question asking about the definition of the characteristic equation. Actually, the characteristic equation of a linear system or process is obtained by setting the denominator of its transfer function to 0. The solution of the characteristic equation, the values for which it is equal to 0, are called the roots of the characteristic equation of the poles of the transfer function. So assume that I have this transfer function, a general form of transfer function. The characteristic equation is the polynomial of the denominator. If I put this one equal to 0, I will find the roots of the poles of the system. For our case, I have transfer function 2 over s squared plus 6s plus 5. So the characteristic equation is s squared plus 6s plus 5. We already find the roots of this one, which will be equal to -1 and -5. So the poles are -1 and -5, and the system is again stable because we have two roots, two simple roots in left of imaginary axis. But if you look at this transfer function, the roots, we have another definition. The roots of nominator will be called the zeros of the system. The zeros of the system doesn't affect at all the stability of the system. The only effect of them is effect on the shape of the response. Again, the roots of the denominator are called poles, and the roots of the denominator called zeros. Poles are important in investigating the response of the system and the stability of the system. The zeros doesn't affect on the stability of the system, but they can somehow affect the shape of the response. So this was the first and second questions from the last sample question. In next videos, I will solve the rest of the equations, specifically for the control design and for both plot diagrams. Have a good time, and if you have questions, please feel free to come to my office or send me an email.